Welcome to Usability and Human Factors Approaches to Design. This is Lecture C. The objectives of this lecture include developing a further understanding of the iterative design process. You should also be able to describe principles of sound design to support usability. In addition, there is an expectation regarding your ability to understand and describe how Nielsen's heuristics and design principles apply to user interface design. The remainder of this unit is focused on design principles. Note that this lecture focuses on general principles. Refer to Component 15, Unit 6 for material specifically related to EHRs and usability, and Component 15, Unit 10 on designing for safety. We'll start by introducing a set of design principles to support usability, drawing on the work of Dix and colleagues. They articulate three top-level principles which can be further decomposed. Learnability refers to the ease with which new users can achieve basic proficiency using a system and hopefully mastery at some point in time. Learnability is especially important in the context of health information technology because systems are often very complex and some time is needed to acquire basic proficiency. Flexibility refers to the ways in which the user and system exchange information, for example, through dialog box exchanges. Robustness is the level of support provided to the user in determining whether they successfully achieve their goals. This includes being able to discern the state of the system and also being able to recover from errors. Learnability can be further decomposed into 5 principles. Predictability is a function of the support provided for the user to determine the effect of future action based on the past. Does the system offer a coherent experience, or is there too much variability? Synthesizability refers to the extent to which users can understand effect of past operations on the current state of system. Familiarity is determined by the extent to which a user's knowledge and experience can be applied when interacting with a new system. People usually choose a certain action based on the knowledge that they have gathered from various experiences throughout their lives. Generalizability is the support for users to learn new facets or components of the system. Consistency in this context is used to refer to commonality in input-out behavior arising from similar situations or similar task objectives. For example, if you click on an object or select a menu, the system's behavior will be largely predictable. In the unit on Usability Evaluation, we discussed Nielsen's usability heuristics. We will discuss them here to illustrate design decisions. These principles have had considerable influence on design and provide guideposts for design decisions. Visibility refers to the extent to which one can discern and comprehend the state of the system. The simplest example is if you are engaged in a 5-step or 5-screen process. The screen should be clearly labeled as 3 out of 5, for example, noting that you are currently on screen and you have 2 more to go. System transitions can be confusing and they need to be made explicit to the user. Obviousness is an important attribute of system visibility. In other words, deep hidden meanings are not appropriate. The questions, where am I? What's happening? What can I do? And what do I need to know? Suggest the need to keep the user focused on the task at hand and that the state of the system should be as transparent as possible. Most users are not interested in simple exploration of a system. Wait states can be very confusing to a user. Some transactions are going to take time and you want users to be able to monitor progress. This image is a glucose and blood pressure upload data screen from the Iterative telemedicine study. The display indicates the process of patients uploading their values from their meters over the networks to a central server. It was a slow process, and the blue bar represents the progress towards a complete upload. If the upload fails to progress, the patients would be clear that their data was not sent. This is valuable feedback. In this lecture, we will draw on a telemedicine study in which older adults with diabetes were given computers, glucose, and blood pressure meters to better manage their diabetes. The participants were general low literacy and were relatively new to computing. Over the course of the study, many design changes were made to better accommodate users' capabilities. In other words, we tried to make the system as intuitive and as accessible as possible for this population. The system should speak the user's language, with familiar words, phrases, and concepts rather than system-oriented terms. It should follow real-world conventions, making information appear in a natural and logical order. One of the most frustrating experiences is if one of your actions causes you to unexpectedly leave the program. For example, as people transition to web-based email applications, they need to remember that closing a window won't only close a message, but will exit the program. Systems should support multiple undos and redos. There are many systems in which backward navigation is not permissible, and this can be very frustrating. You may have heard a lot about standards in learning informatics. Usability and design are no different. As discussed previously, consistency is very important in promoting system learnability. Some systems have multiple modes. For example, there are clinical information systems that will permit you to browse and search information. However, if you want to enter data, you will need to switch to another mode. This can be very frustrating to the user. The law of least astonishment states that when two elements of an interface conflict or are ambiguous, the behavior should be that which will least surprise the user. In particular, a developer should try to think of the behavior that will least surprise someone who uses the program, rather than that behavior that is natural from knowing the inner workings of the program. When it comes to using computers, surprises are generally not welcome. To the extent possible, a system should endeavor to prevent users from making mistakes. They can be especially costly in the context of patient care. Some advice is to make bad things hard to do, such as closing out a program without saving the data. In addition, it is important to identify errors early so that the system can prompt a user before a submission. Some actions are irreversible and may inadvertently result in the loss of data. A system should warn the user about such actions. Lastly, people tend to think that escaping a dialog box immediately cancels an action when in fact that is not always the case. Errors are inevitable and can be major irritants depending on how the system handles them. Systems should help users recognize, diagnose, and recover from errors. Error messages should be expressed in plain language without recourse to codes. The very worst error messages are those where no problem seems to exist. It is always best to suggest a solution or course of action rather than just stating the problem. Not too long ago, meaningless error messages were very common. That still happens, although much less frequently. Note in particular the last one. Error, the operation completed successfully. The importance of placing an emphasis on recognition is a hallmark principle of human factors, as well as human-computer interaction. Accentuating cues in the interface serves to minimize users' memory load. It is advisable to make objects, actions, and options visible in the graphical user interface. Cues in the interface should guide a user towards a series of steps, and the user should not have to remember information from one screen to another. This is especially important in interfaces for computerized provider order entry (CPOE) systems that involve the management of a lot of information. Using icons instead of words or in addition to words can facilitate recognition. Like anything else in design, you want to test whether icons are readily discernible and not too cryptic for most users. When systems are too rigid and inflexible, they tend to frustrate users, especially experienced ones. The following are some ways to promote flexibility and efficiency. Allow users to customize frequent actions. Employ keyboard shortcuts such as Control-P for printing, and allow macros for repetitive tasks. Programmable interfaces afford users the ability to customize displays. There are a growing number of tools that make this easier. More than any other company, Google, with its Spartan-like search engine interface, has embraced the minimalist design aesthetic. Screen content should relate to users' goals. Many users will not be able to separate relevant from irrelevant, and added clutter imposes a memory load on the user. Design and decoration should enhance visibility. The removal test. 1. Remove item. 2. Test application. And 3. If the application still works, leave it out. Of course, this is not meant to be taken literally or to be applied in all cases. It's the principle of pruning that which is not necessary that is operative here. Clarity of message and readability should be the order when it comes to issues of color selection. Design in black and white and use 4 or fewer colors. Use color consistently, avoid color opposites, and be careful of unintended color meanings. Sound help for users and documentation are generally undervalued. Keep in mind that no one reads the manual until something breaks. So, plan instructions for problem solving. Stepwise, pictorial instructions are very useful. In addition, testing your documentation should be a part of usability evaluation. As described earlier, I am now going to present a brief case study that focuses on iterative redesign of hardware and software designed for a remote telemedicine project for older adults with diabetes. The IdeaTel project was a large-scale, home-based telemedicine project for medically underserved diabetic patients. Usability testing revealed a range of user problems that impeded productive use of the system. Consequently, the project team re-engineered the system in significant ways. Many changes to the design were made based on a better understanding of the study population, which of older adults. Many of them were limited in their literacy, and the vast majority of the population was new to computing. The interface was simplified over a series of iterations. The size of the text and interactive elements, such as buttons, grew in size to accommodate vision constraints. In addition, there was a significant hardware change as illustrated in the next slide. The 2 images represent 2 generations of telemedicine system. These are both workstations for patients to communicate with nurse case managers and to access various tools and educational materials to better manage their diabetes. The screen on the left is a first-generation old-fashioned system. The one on the right is a touchscreen system that was designed to be more intuitive and physically easier to use for elderly patients with low computer literacy. The first system was a conventional Windows icon and mouse-based browser. The mouse presented significant difficulties for many of the users who were older adults. The project embraced a touchscreen model that proved to be significantly easier to use for many of the participants. This is an illustration of the original patient interface. The small type and cluttered look presented problems for users. This second slide presents a modest iteration on the original design. Basically, everything is a little bigger with better spacing. To accommodate the new screen system, additional changes were made to the system. The overall look and feel has been redesigned, and a set of tools, e.g., to view blood pressure values over the period of a week or 2 weeks, were introduced that would make it easier for patients to view their data over time. This further improved the system and the patient's experience. This is an example of an interactive screen. Participants were given a pedometer, encouraged to walk daily, and entered their steps into the computer using this display. The display was designed to resemble a computer, which is a familiar object. There was only one problem. The number of steps field was zero padded, meaning zeros were at the beginning, to resemble the actual device. As it turns out, this is very confusing for users. In general, the iterative changes in design resulted in a better computing experience for users. This concludes Lecture C of Usability and Human Factors Approaches to Design. Today's lesson focused on design and specifically principles to guide design. It should be noted that learnability factors are important and often overlooked.